Okay, so guys, assuming that we're done with this, again, as I suggested, you need to grab something you can take notes with. You need to grab something you can take notes on. And you need to grab your calculators. If you don't have a calculator, you can probably follow along with the math today. So guys, today what we're going to do is we're going to wrap up the unit. And we're actually going to wrap up the unit by circling back around to a concept that you have heard glossed over perhaps multiple times. The first time that you heard about this concept in here, it was actually in the Eyes of Nye video that we watched. But guys, you heard this word referenced in multiple contexts. Guys, today what we're going to do is we're going to dig into it. And not surprisingly, that thing is half-life. So guys, today is the 30th. The concept is half-life. Now, sort of setting the stage for what we're going to do today. Guys, when we talk about half-life, what we're doing is we're answering a question that is actually a follow-up to a first question. Don't write this down. But guys, this is where we're headed. And we're going to spend a second in review for the test as we talk about this. So, guys, when we think about half-life, we're really thinking about what happens to things when they decay radioactively. Now, guys, when we talk about decay, let's make sure you're up to speed. Guys, on Friday, how many different types of decay are you going to be tested over? 3, alpha, beta, and gamma. So guys, let's go over alpha first. So guys, these are the things that you need to know about alpha decay. What is an alpha particle? It is a helium nucleus. It is made of 2 protons and 2 neutrons. Thought number 2, how do they move? And the answer is slowly. They are large, slow particles that do not penetrate well at all, but they still come out of the nucleus. So guys, when they come out of the nucleus, thinking about atomic mass and atomic number, when an alpha particle goes, what happens to the atomic number? Down by 2. What happens to the atomic mass? Down by 4. Questions on alpha decay. Okay, now beta decay. Guys, what is a beta particle? It is an electron that comes out of the nucleus. But wait, I didn't think there were electrons in the nucleus. There aren't. There are no electrons in the nucleus. So what magic thing happens in the nucleus when the electron goes out? A neutron becomes a proton. Now guys, these electrons are small and fast. They are more penetrating. But guys, when something goes through alpha decay, again, same game. When something goes through alpha decay, what happens to the bottom number, the atomic number? Up by 1, right? Or I'm sorry, beta decay, the bottom number goes up by 1 and the mass doesn't change. Are we good? Okay. Then guys, gamma decay. When something goes through gamma decay, it's not a particle. It is the release of energy as the nucleus relaxes. And because it's not a particle, it doesn't change up the makeup of the nucleus. You guys good? Okay. So guys, with that said then, what's that? Yeah. Yeah, so the idea is in beta decay, you've got the atomic mass, the atomic number. In beta decay, the bottom number, the atomic number goes up by 1 because a neutron becomes a proton, and the bottom number tells us the number of protons. It's the atomic number. Then the mass doesn't change because neutrons and protons weigh the same. Is that okay? Okay. Guys, and so I'm glad you asked. Any other clarifications y'all need? We okay?
So can protons turn into neutrons?
They can. I'll talk about it briefly. So guys, Corbin asked the question, can protons turn into neutrons? And the answer is yes. And it happens through a process called electron capture. Literally what happens is a proton in the nucleus sucks an electron out of orbit. It literally pulls in an electron, and that proton plus that electron becomes a neutron. We don't talk about it when we talk about decay, because decay means to give away, and this is taking in. So it's not technically decay, but it is another nuclear change process. We just don't deal with it in this context. But yeah, it happens a lot, actually. The things that tend to be alpha decay participants also tend to go through electron capture. Yeah, it's kind of cool. Okay, so guys, this then is the idea. So we understand, we're talking about this idea of what happens to things when they decay. You should know the answer to the first question. Guys, when atoms go through decay, what happens to them? They change into other elements, right? They don't disappear, they don't go away, they simply turn into other elements. But guys, the question that we're going to address today is this: how long does it take? How long does it take for uranium to go through alpha decay? How long does it take? And guys, the answer is actually what we're talking about today. So how long does it take for these processes to happen? The answer is half-life. And this is where you want to start taking notes. So guys, when we talk about half-life, we need to define it. And I would strongly encourage you to write down these notes word for word. So guys, this is the idea behind half-life. We're going to build up to the definition. So it goes like this. Half-life is a measure of radioactivity. So what is radioactivity? Radioactivity are the alpha and beta particles that are given away during decay. So guys, half-life is a measure of how quickly these particles come out. So this gets complicated. And it gets complicated because of the word spontaneously. Guys, the problem is this. Inside a chunk of uranium or plutonium or thorium or whatever it is that's decaying, guys, the atoms in that sample decay spontaneously. So the atoms in radioactive materials spontaneously just break apart. We call that decay. So right now, guys, these uranium atoms inside this chunk of ore are spontaneously decaying. So if we could look at just one of these atoms, we have no idea when it's going to decay. Could be now, could be later, could be never. We just don't know. Where'd it go? Did I lose a little bit? I felt it. Maybe not. We're okay. So guys, we don't know when this is going to happen because it's spontaneous. So what do we do about that? Well, guys, the reasoning goes like this. We cannot tell when an individual atom is going to decay. Because it's spontaneous, it's random. Because it's random, there's no way to predict. So guys, we can't tell you with any certainty when any particular atom is going to decay. But what we can do is this. We can talk about fractions. So guys, what we do is we leverage the idea that while we can't tell when one atom will decay, we can tell when a fraction of them will decay. And do you want to hazard a guess at the fraction we talk about? That's where the name comes from. We talk about halves. So guys, half-life then, by definition, half-life then is the amount of time that it takes half of the atoms in a piece of radioactive material to break apart. That is going to be our working definition for half-life. It is the amount of time that it takes half of the atoms in a piece of radioactive material to break apart. Now guys, fundamentally, that's all we're going to do today. You're done. If you really understand this, you're functionally done. But you don't yet understand it at the level that you need to. So guys, what we're going to do is we're going to approach this idea from 4 different angles. We're going to look at it visually. We're going to look at it through a video. Then we're going to look at it graphically. And then we're going to look at it mathematically, which is why you grabbed your calculators. So guys, this is the big idea, and this is half-life. But guys, before we dig into this, we need to avoid some misconceptions. The misconceptions come in the form of questions. So guys, question number 1 is this. Where do the radioactive atoms go after they decay? So when one of those radioactive uranium atoms decay, where does it go? Where does it go? Still there. But what's different? It's not uranium anymore. So guys, when these elements go through radioactive decay, they don't go away. They are still there. They have simply turned into other elements. So guys, this then becomes the idea, and this is the first thing that I want to help you understand. After each half-life, a half of the original sample is still there, and the other atoms, the atoms that have changed, are still there too. They're just a different element. So guys, once you've got this written down, this is where we're going to start chipping away at this. We're going to chip away at it visually, through video, graphically, mathematically. We're going to chew on this from all sorts of different angles. So when you're done with this, you can settle in for a moment, and we're going to take one approach at your understanding this idea. But we'll wait until you're done. Or at least caught up. You guys okay? Not yet? So that's why I glove up. So the thing with this uranium is those alpha particles are low energy enough that, frankly, you know how we said that they can't get through your hand? They actually can't get through your dead skin layer. They're so big that they actually don't even penetrate your skin. And so consequently, just touching this is no big deal because it doesn't even get into my live flesh. It all sticks in my dead skin. The problem is if I were to ingest that uranium, then it's down in amongst my organs, and then it can irradiate my organs. And that's why I glove up, not because I'm worried about now, but because I know I'm about to eat lunch. And if I grab a sandwich with that stuff, now I'm eating it, and that's where it gets dangerous. So that's why I glove up. You guys ready to go? Okay, so guys, watch and learn. Here's the idea. So this is how this concept goes. So we know that this isn't true, but we are going to pretend that this is 100% uranium. So this is enriched uranium ready to go in the bomb. This is 100% uranium. It's not, but we're going to pretend it is. But let's give it a mass. Let's say that this is 100 grams of uranium, and it's nowhere near that, but let's pretend. Now, guys, in order for you to understand this concept, here's what we're going to say. We're going to say that this is times 0 right here, and this is 100 grams of uranium. Now, over here, this ledge right here is going to represent the moment when all of that uranium is gone. Okay, it's all decayed and it's all gone and there's no more uranium left. Now guys, will the rock disappear? No. Understand that if it's going through alpha decay, it will be a big chunk of thorium. If it's going through beta decay, it'll be a big chunk of neptunium, but there'll still be something there. It'll still weigh 100 grams. Minus the mass of the protons and things not yet that leave. So, guys, we've got pure, and over here we've got none, gone. Okay, now here's the idea. We're going to make up an easy number. Guys, let's say that this weighs 100 grams, and just making up a number, let's say the half-life is 5 years. It's nowhere near that, but let's just say 5 years. So guys, this is the idea. We're now going to track this through time. So how much uranium? 100 grams. 5 years is the half-life. So guys, after 5 years, let's say it's alpha decay, so we've got this uranium turning into thorium, and after 5 years, we have now gone through one half-life. So guys, how much of this is still uranium? 50 grams, a half, right? Now, what do we have over here? 50 grams of thorium, or whatever it turned into. But guys, that's the idea. After one half-life, half is gone, half remains. Now, here's where this gets interesting. How long did that take? 5 years. Now, guys, after the next 5 years, is it now totally gone? No. And that's the idea behind half-life. Guys, the idea is this. After 5 years, we've only got half left. And because we've only got half left, it is decaying slower. So after the next half-life, we don't lose the other half. After the next half-life, how much do you think we lose? Half of the half, and we end up here. So now we have 25% left, 25 grams, and how much is now thorium? 75 grams. So now we're at 2 half-lives. Then guys, 5 years later, we still have some left. How much? 12.5 grams. But guys, let's do it as fractions. So we have an 1/8, and then we have a 16th, and a 32nd, and a 64th, and a 1/28th, and a 2/56th, and a 10/24th. But guys, we never get to the ledge. You never, for those of you that understand math well, this is an asymptote. We never reach the wall. You never run out because you can always have an ever-decreasing half of the half. And now you're thinking, wait a second, that's really weird. But guys, if you're a football fan, you already understand this. Because if I'm a football team and I'm going this way, and if I'm on the 9-yard line, and if I commit holding, what's my penalty? It's not 10 yards. What's my penalty? Half the distance to the goal. And what if I do it again? Half the distance to the goal. And what if I just keep getting holding penalties? Will I ever get a safety? You can never be penalized into your own end zone because there's always a half of an ever-decreasing half, and you never get to the end zone in the same way that you never run out of atoms. Do you understand the concepts? Antonio, you wanted to ask a question? Okay, does the concept make sense, y'all? This idea of halves of halves of halves? Is that okay? So guys, if you understand that visually, let's now take a swing at this through an interesting video that actually provides sort of a terrifying twist to this. Our good friend Bill Nye, the science guy. So guys, this is the first time you encountered the idea of half-life in this class. It's the first time the word half-life was floating around in the air. And you may remember that it was when Bill was having a conversation against this obviously very politically charged individual that kept calling humans a species. Do you remember that guy? And he was talking about plutonium, and here's what they said.
Plutonium is the most dangerous thing that human beings have ever made. It will probably be our demise. A millionth of an ounce, the size of a speck of dust, if inhaled, will cause...
Okay, so let me start over.
Plutonium is the most dangerous thing that human beings have ever made. It will probably be our demise. A millionth of an ounce, the size of a speck of dust, if inhaled, will cause lung cancer. A few pounds, the size of a grapefruit that you can hold in your hand, will bring down a city if used in a nuclear weapon. And it has a 24,000-year half-life.
24,000 years. So guys, the half-life of plutonium is not 5 years, it's 24,000 years. Keep that number in mind.
We measure radioactivity in what's called half-lives. You see, the atoms in radioactive material spontaneously just break apart or decay. Now, we can't tell when an individual atom will decay, but we can tell when a fraction of them will.
You guys having the deja vu moment? Because all the notes that you wrote down at the beginning of class about half-life was actually a transcript of this video. Once again, verifying that all truth comes from Bill Nye.
So a half-life is the amount of time it takes for half the atoms in a piece of radioactive material to break apart. Now, plutonium has a half-life of 24,000 years. So let's say this red water is the plutonium in a spent nuclear fuel rod fresh from the reactor. Well, after one half-life, 24,000 years, diluting this water by half, it looks like this. After two half-lives, 48,000 years, it would look like this. After 10 half-lives, 240,000 years, the water starts to look pretty clear. Now, plutonium is notorious. It's especially radioactive. It's 20 million times more radioactive than uranium dug from a mine. You see, we're not talking about potato salad left out in the sun. We're talking about plutonium. Now, the legal requirement for storing this material is only 10,000 years. That would be over here someplace. That's not even half of a half-life.
Guys, do you feel like you understand that video now in a way that you didn't before? Go ahead.
So is it all like the all your uranium go away like once it hits like 24,000 years, or does it slowly go away?
That's a great question. So it doesn't happen all at once. The key word here is spontaneously. So if you have a chunk of plutonium or uranium or whatever, that is always breaking down, and it's breaking down fastest at first, and then over time, the rate at which it breaks down slows down. And so the idea is in that first half-life, 24,000 years, half of it goes away. In the next 24,000 years, only a fourth of it goes away because there's less of it, so it breaks down less quickly. But the idea is that it's always breaking down over time, really fast at first, slowing down over time, but it's always taking place. Yeah, go ahead, Corbin. Just a second, Antonio.
Lots of energy created when it's decayed.
That's a really interesting question, and the answer is not like fission and fusion, lots of energy, but my watch, do any of you actually have a watch with hands and they glow? The reason is because there's actually a little bit of thorium in the hands of your watch hands, and actually that glowing is actually energy being released as the thorium is breaking down. So there are small amounts of energy, not like it's going to give you cancer or burn you or anything like that, but it does produce energy. Even so much that we're talking now about if we do end up populating Mars, what they want to do is they will take little nuclear reactors to generate the electricity, but those reactors release heat. The energy as but that's a bad example because that's fission. Never mind, bad example. But you also do get a little bit of energy out during decay, just not quite as much. So go ahead, Antonio.
Since we're not really able to measure it exactly on the reactivity,
Yeah,
and since we only measure half-life,
Yeah.
which makes it so that the atom never actually sees us.
yes.
Does the real atom actually has a point where it sees it?
That's a brilliant, let me do this. It's a brilliant question to which there's a really cool answer, but I think that we can answer that question better 2 slides from now, because we're going to throw up an image of this, and I think we can answer the question then. Will you let me table it for a second? Okay, so guys, do this with me. You said that you feel like you understand this better now. If you do, then let's have this conversation. So looking at this, guys, can we call this an analogy? What in this analogy represents the plutonium? The red food coloring. So how did Bill create this analogy? And what he did is he took this red food coloring water and he diluted it in half, diluted it in half, diluted it in half, diluted it in half. So each time it's half as concentrated. So this is full concentration. This is a half, a fourth, an eighth, a 16th, a 32nd, a 64th, and so on. So guys, the red hue, if you will, is the plutonium. So guys, what do the cinder blocks represent? 24,000 years. Guys, those cinder blocks represent half-lives. Now let me ask you a question. Moving to the right, guys, if that red dye were poison, at what point would you be willing to drink the water? Well, so I still see red there. I still see a red tint there. Maybe? 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 Maybe on the very right, you mean? Oh, over here.
Sure, the right is.
Oh, over here. But guys, here's the thing you got to understand. If that red stuff is something that you don't want near you, this represents almost 250,000 years from now. 240,000 years. Now guys, this is where this is about to get sobering. If you really understand the video, let's do it there. What does Bill's hand represent? How long we need to be able to store this material. And guys, if you don't think this is important, this has the chance to change your life. And I'm not trying to be dramatic. Guys, Bill's hand represents government trying to do science. And this should terrify you. Because guys, Bill's hand represents, and this is still true. This video is about 6 years old, but this is still the case. This law has not changed. Guys, Bill's hand represents how long we've got to be able to store this plutonium. 10,000 years. Now guys, how did we come up with that number? Do you remember? Because it's actually kind of crazy. How did they come up with 10,000 years? No. Let me do this. Does 10,000 years have anything to do with the science behind what's going on? No, because guys, that's not even a half of a half-life. This stuff is still wacky radioactive 10,000 years from now. It will kill you then just like it would kill you now. So that number is not based in science. Where does it come from? Do you remember? Yeah, here's what they did. You know those columns, those canisters we got to put the plutonium in? They studied these canisters, and their studies were showing, because this is nuts, this is how our government thinks. What it showed was, the governmental studies showed that those canisters would fail in 11,000 years. So they said, if they fail in 11,000 years, let's make the law 10,000 years so that we can legally put the stuff in the containers. Do you see the flaws in that logic? Guys, we know 11,000 years gets us almost nowhere, but in order to be able to put the stuff in the containers, our government made a law that we've got to be able to store it for 10,000 years, and now all of a sudden our 11,000 year containers meet the law. But guys, that is based on legislation and not on science. And guys, if you don't think this applies to you, these same sorts of shenanigans are going on right now with climate science. We've got people that don't understand science passing laws. They should have taken my class. They would know better. So guys, this is crazy. This makes no sense. Yeah?
Can't this class be called political science?
I hope not. Go ahead. Well, and that's the thought, right? So, and that was the thing that was interesting. Just a second, Matthew. The question is, couldn't we just put it in a new container? Let's talk about that. So if the containers last 10,000 years, we would have to do that 24 times until this stuff is safe, right? So, but we could do that. We could build 24 new containers. And it's interesting because I would propose that is actually the argument that TED Talk dude was making. You notice he never talked about what to do with the waste. And when he did at the very end, it was only a very short comment that basically said this stuff is safe, right? And technically he's right. We have a container that it'll sit in for 10,000 years. But then what? So the real question, and guys, some of you mentioned this, I've read over your papers. Some of you mentioned this in your papers, that idea of, is storing this stuff really an issue? Because that's the question we've got to answer is storing this stuff really an issue? And maybe in 10,000 years, we'll know how to get rid of it, but we're not sure. Go ahead.
That's what I was going to say, like 10,000 years, that's a long time.
It's a long time. Yeah. Exactly, right? I mean, we might be able to solve this problem, or we could all be gone. right? I mean, given the length that civilizations persist, the United States is pushing the outer limits in terms of how long civilizations tend to stick around. And so what if we're gone? What if we go away and all of a sudden we've just got all these things laying around?
It's probably just like.
What's that?
It's just like, I think it's because how people are like. The one that hunted.
Absolutely.
It's gonna be like.
Sure. Yeah, it's a question of perspective, right? What does 10,000 years mean if you're 16? Go ahead.
What do they mean when they say the container's going to fail?
That's a great question. So what does it mean when the container will fail? And it literally means that. So these containers are made of a mixture of stainless steel and concrete. And if you've ever driven down I-15, you know what we're talking about, because when you drive under a bridge and look up, those suckers are crumbling, right? It's a huge problem right now because most of our highway infrastructure was built 50 or 60 years ago, and those things are starting to crumble. Concrete doesn't last forever. Even when it's contained in metal or contains metal, which our bridges do, that's what these things literally fail over time. Yeah, they break apart. So, guys, do you understand the idea now in a political context? Okay, so anything else you want to chat about here? Okay, so now we're going to go in an even different direction. So we've talked about this visually. We've talked about this politically. Now, guys, we're going to talk about it graphically. And guys, the conversation goes like this. When you ask a scientist, how do we represent half-life? This is what they will present you. Guys, again, moving towards getting you better prepared for things like the ACT, you need to be able to wrap your arms around graphical representations. So guys, here's how this goes. This is time, this is amount. So here we have no time and all of our stuff. And as we move throughout time in half-lives, the amount of stuff is going down. Here's my question. Guys, where on this graph is the floor in this analogy? Where on this graph is the floor? Which axis? The X or the Y? It's the Y. Guys, here's the idea. On the Y-axis, you see a half, a fourth, an eighth, a 16th, and so on. So guys, on the y-axis, you've got a half, a fourth, an eighth, a 16th, and so on. So guys, that's where we see this ever-decreasing fraction. Where do we see the 5 years? That's the x-axis. That's 5 years, 5 years, 5 years, or whatever we said. But guys, this is the same concept that we talked about on the floor. I would propose the floor is easier to understand. I don't prefer this. So let me offer you this. I would suggest this is getting closer. Again, we've got time, and each one of these represents a half-life. Here we've got numbers of atoms. They just picked a unit, millions. But now we've got things that actually represent the numbers of atoms. So each ball is 100,000. So we've got 200, you get the idea, fractions of millions or 100,000s. But guys, looking at this, I would propose to you that if you understand half-life, this thing is riddled with errors and misinformation. What do you see? Because where are the gaps in the way this represents half-life? Go ahead.
It says years well, they are evenly spaced.
Right, and I agree with you. Good, Ethan.
The pictures, it's suggesting that it only half-lives, not the half-life.
Yeah, good for you. And that was what you were getting to as well. This idea that it seems like it waits and then it drops, and then it waits and then it drops. Where in fact, that would be nice if they had, great observation, that it would be neat if they had balls all the way along, showing that this is always decreasing. That's a great point. What else do you see, guys? What are other deceptions? Problems. Just a second, Emily, go ahead. Say it again. Okay, so this guy's cut in half, that guy, and we know we can't have fractions of atoms, right? But if we understand that each one of these balls represents 100,000 atoms, then we might be okay with fractions of 100,000, right? Emily, go ahead.
The first stack, the top atom is like above the
Mm-hmm.
second stack. It's like
I hated that. I wanted that line to at least be here, or at least shorten the stack so the top of the ball was there. I totally agree. What about this one? So if this is 10, what's that? 5. If this is 5, what should that be? 2.5. And it doesn't look like 2.5 to me.
3, 2, 3, 4, 5, 6.
Again, a mistake. Anything else y'all see? Because you haven't even gotten yet to the thing that I hate the most. Say it again.
Shaded the grass. I don't know.
Do you struggle with that? Maybe. I mean, we could have millions of atoms, and this could take billions of years.
What do you hate the most?
Yeah, guys, this is the part I hate the most. Where's this stuff? You should have said it. What are you thinking, Abby?
well,
Emma. I just called you Abby. I'm so sorry, Emma. Sorry, her sister. The reason is because I was just... Sorry, say it again. What?
the y-axis line, but not the x-axis.
Okay, so what would you like to see? Okay, so you'd like to see something here. I don't think that was quite where I was headed, but it's not wrong, and I agree with you. But I still have a big old problem. Go ahead, Isaac.
Still, the matter that's like being destroyed is different stuff.
Yes. I would have really loved for them to have done, maybe even pick a different color and show, guys, that stuff is still there. It's something different, but this makes it look like it decays and just disappears. And that's not, and many of you would have looked at that, and if I hadn't pointed it out, maybe subliminally you would be thinking, oh, when it decays, it's just gone. Because it's not, it's still there, and many times it's still radioactive. So, how do we fix that problem? Guys, this is the best I could find. This is, sounds weird, but my favorite. This makes sense to my brain, and Antonio, now we can answer your question that we tabled. So guys, here we have time, numbers of half-lives, here we have the amount that's left. So we have 100. After one half-life, how much do we have left? 50. But now we see the 50 that changed still represented now as gray. Then after another half-life, we have 25 left, 75 now represented as gray. Here it kind of falls apart because they don't show us 12 and a half and then the remaining fraction. But we're seeing 12, I think, in 88. But now we finally see that the stuff that's changed is still there. It just hasn't gone away. So now, Antonio, to your question, what if we keep going? Won't we eventually get to the point where we've got one atom left? And when we have one atom left, when that thing decays, won't we have no atoms left? And the answer is, in theory, yes. In practice, it never happens. And the reason is because it's not about ones, and it's not about tens, and it's not about thousands, millions, billions, or trillions. Even in this silly little rock, even in this chunk of uranium that we have right here in front of us, guys, there are more uranium atoms in that chunk than there are stars in the sky. And when we are talking about numbers of atoms on that order, while practically it makes sense that we could lose that last one, we never get to that last one because we're starting with so many to begin with. So having that conversation is unnecessary because it never happens. Is that okay? Do you buy it? Okay. So guys, here's where we're at. We did it visually. We did it video politically. We've now done it graphically. We have one more pass at this. You guys good up to there? Okay. Guys, we're going to do this mathematically. Join me. And guys, this is not me being prideful. This is me warning you. I am really good at this. You have no idea if you're good at this until you try. And guys, this is what typically happens. Some of you get that, and you understand homework is your opportunity to try, and taking notes is your opportunity to help yourself do better with homework. But some of you are going to sit back and go, I got this. You don't got this. You got that Knappenberger got this, but you ain't got nothing. And then, guys, when you sit down to take the test, you're going to go, yeah, I guess I didn't get this. So, guys, please, if I may use the word with you, don't live vicariously through me. You need examples in your notes. And you have to do the homework before Friday, or you gonna get your trash kicked. Okay? So with that said, guys, let me show you what we're doing. In order to understand half-life mathematically, we need two equations. Here's the first one. Write it down with me. It simply says this. N is equal to T divided by T 1/2. Please remember in this class, you do not memorize equations. It will be given to you on the test. You just got to manipulate it. But guys, what do the variables mean? The answer is this. N is the number of half-lives. T is the time that the sample sits around. And T 1/2 is the time of a half-life. Now, guys, I would encourage you to not defile your notes. But let me show you how this works. 24,000 years. That is the half-life of plutonium. Now, if a chunk of plutonium sits around for 48,000 years, how many half-lives did it go through? Get the idea? Pretty simple. Now, guys, the other equation, which is a little more complicated, is this one. Percent remaining is equal to 1 over 2 to the n. And guys, that n is an exponent. It's the best I could do to get it to become a superscript. But guys, that n is an exponent. And again, n is the number of half-lives. Now, I showed you what the previous equation means by simply showing you 48,000 divided by 24,000. What does this equation mean? Guys, let me show you, but please don't write this down. So what does this equation mean? Well, this is what it means. We can count the number of half-lives, 1, 2, 3, 4, 5. The question is, what percent remains at the end of those time periods? So guys, to do this, you plug these numbers in for n. But guys, this is not times n, this is to the n. So, what is 2 to the first? 2. That means we've got a half. What is 2 to the second? 2 times 2 is 4. That is a fourth. What is 2 to the third? And don't say 6. 2 times 2 is 4. Times 2 is 8. That is an eighth. And then a 16th. And then a 32nd. And that's where those fractions come from mathematically. Do you see the relationship? Yes?
Do we have to write it in fractions, or can we just write it in percent?
That's a good, well, I would strongly encourage you to do this as fractions simply because it's one less mistake to make. Because converting this to a decimal or a percentage, if you convert wrong, you're going to get it wrong. I leave them as fractions. So, guys, with that said, using these equations, this is actually the type of problem that we can solve. I would suggest that you not write it down. If you want this as a reference, you can print the notes. But we are going to solve this. So, guys, read along with me, and you really want to write down the answer. 50 grams of plutonium decays for 72,000 years. I picked plutonium because it's familiar. Guys, the question is this. What mass of plutonium remains at the end of this time, remembering that plutonium has a half-life of 24,000 years? So, picture it. You've got a 50 gram chunk of plutonium. It sits around for 72,000 years. How much of that is still plutonium at the end of that time? That's what we're going to figure out. So guys, the very first thing you want to do is this, and you can fight me on this if you want, but it's at your own risk. Guys, the very first thing you're going to do is write down the equations, both of them, every time. Just write them both down. This will save you. Write down the equation. Now, guys, the next thing that I would encourage you to do is this. Figure out what you're trying to figure out. What are we solving for? Read the question again. What are we solving for? Yep. So, guys, the question that we're solving for is this. What mass? But now we've got a problem, because there is no mass anywhere in these equations. So what can we solve for that gets us closest to mass? Percent remaining. So guys, the idea is this. If we know the percent remaining, that will be a percent of 50 grams, and that will let us figure out the mass. So, guys, in order to, and follow the laser, here's how this goes. In order to solve for percent remaining, what do we need to know? N. But we don't know N. So now, guys, we jump over to this other equation, and in order to figure out N, we need to know these. Do we know time, and do we know time 1/2? We do. So, guys, N is then equal to, what is the time? How long does this sit around? 72,000 years. What is the time of a half-life? 24,000 years. And we can do that math. So guys, 72,000 divided by 24,000 is 3. Now guys, here's the thing. The numbers that Miss Call and I will give you in homework and on the test, and Ethan, this actually gets to your point a minute ago. Guys, when we give you the numbers, they will always work out to be whole numbers. In the same way that those columns were only the whole half-lives, there won't be fractions. Guys, we will never give you lengths of time that result in fractional half-lives. It makes the math too messy. So guys, what do we then do with this? Plug it in for N. So we go 1 over 2 to the third. Some of you are then going to write 1/6. No, it's 1/8. So Antonio, this is then to your point. You could turn that into a fraction and make it 12.5%. But guys, understand this is not your answer, right? It is 1/8 of 50 grams. So the math looks like this. The mass remaining is equal to 50 grams times 1/8. And this is why I would encourage you to not turn this into a decimal. Just leave it as 1/8. And then guys, it's really just 50 divided by 8. And we are going to let the mass limit significant digits because we manipulated the numbers to make this a whole number. So we're going to count that as perfect. So guys, we're going to limit this to 3 significant digits. And the answer is 6.25 grams. So that is one of the 2 kinds of problems that you'll be solving relative to this half-life stuff. Because what I'd like to do is show you an example of the second type and then give you a pretty good chunk of time to work on your homework so that you can hone in on this as you're getting ready for the test on Friday. Questions on this process? Y'all okay? Okay. So that's the bottom line, Emma. Yeah, so you can just ignore the fractions. The reason is this. We made up this number, and to be honest with you, this number's kind of made up too. It's not exactly that. Even from the Bill video, it's not exactly that. So these are sort of adjusted to give you a whole number. So we're just going to not let that be significant. Guys, okay? So guys, this is harder. Goes like this. This is as hard as these get. Read it with me. So you've got 100 grams of molybdenum-91. And that sits around and decays for 60 minutes. At the end of this time period, you end up with 6.5 grams of that left. What is the half-life of molybdenum-91? So guys, you read this, it's the test, you panic. What do you do first? Write down the equations. Because I promise you, you get to AP Chem, some of you could muscle through this in your head. You get to your college chemistry classes, when you get stuck, I want you to have this moment where you go, what do I do? Write down the equations and then write me an email and tell me thank you. Guys, write down the equations. You're welcome. Okay. Now, guys, what's the next thing you do? What was after you write down the equations? What did we do in the previous problem? What's the next thing you do? What are you solving for? What is the half-life of this isotope? Guys, where in these equations is half-life? Right there. Circle it if that's easier. So guys, now what you do is you allow these equations to provide you a path through the problem. So guys, we know that we're solving for this. So in order to solve for this, what do we need to know? The other two. So, do we know time? Do we know how long this sits around? Write it down. 60 minutes. Do we know the denominator T1 half? No, that's what we're solving for. We're going to call it X. Now guys, this is where this becomes interesting. In order to solve this, we need to know N, but do we know N? No. But where can we get it? The other equation. So guys, we're just going to leave it for now. You don't need to do the question mark. But that's our question. How do we get N? So then we look at this other expression, and the N is right there. But in order to know that N, what do we need to know? Percent remaining. Where is the percent remaining in this equation? It's a ratio. It's the mass before and the mass after. But guys, here's the trick. It's always little number on top, big number on the bottom. You may want to write that down next to this so you don't forget. You can just write down small on top. The small number always goes on top. The big number always goes on the bottom. Now guys, here's the trick. This is equal to 1 over 2 to the n. And I know that some of you in this room have pretty wicked math chops. You're good at math. And guys, if you look at this mathematically, I saw your picture, congratulations. Guys, if you look at this mathematically, you may know that the way to solve this is actually by taking the base 2 logarithm. Right. We're not going to do that. Guys, this is the way we are going to solve these. Here's what you're going to do. We picked numbers that don't require logarithms. So this is what you're going to do. You're going to take this fraction and you are going to simplify it. You will do that by dividing by the numerator in both instances. So you are going to divide the numerator and the denominator by the numerator, simplifying the fraction. So when you do that math, what does the numerator turn into? 1. What does the denominator turn into?
16.
Yep, 16. So guys, why is that magic? Well, remember what it's equal to. It's equal to 1 over 2 to the n. And this denominator will always work out to a whole number because we picked the numbers. It will always work out to a whole number. And then, guys, you can solve this for n simply by muscling through it in your brain. And n is not 8. What is n? And guys, do this on your fingers if you need. 2 times 2 is 4, times 2 is 8, times 2 is 16, and then the number of fingers that you put up is n. So 2 times 2 is 4, times 2 is 8, times 2 is 16. That means n is 4. 2 to the 4th is 16. Now guys, and I was especially proud of this. Watch. Ready? What do we do with the 4? Check this out. Put it there. Huh? Oh yeah. Now guys, here's the problem. And for some of you, this is not your fault. But I've seen this earlier in the year with you. And frankly, I just kind of made me cry on the inside. That was horrible of me to say. I'm sorry. Some can't solve this. And guys, it's not your fault. But some of you can't solve this. So let's talk about how to solve it. So guys, in order to resolve this for x, I know math, I don't believe math teachers talk about this anymore, but you multiply both sides by x. We used to call it cross multiplying. So you get 4x is equal to 60. Did you still talk about cross multiplying?
We don't really call it, but also
But how would your math teachers describe that? Multiply both sides by x? Okay. Then guys, we would then divide both sides by 4, and functionally you get x is 15. So just a second. That then is the answer to the question, how long is a half-life? The answer is 15 minutes. Corbin, go ahead.
So with the 6 minutes on top,
Yeah.
would you not have to convert it to like an hour?
No, so your answers for half-life will always be whatever the units are that are given. Okay. Okay.
Could you solve the 4? So like, if you were to
Could you just go from here and say 15?
like, with the original equation method,
Here? Yeah. Oh, could you switch these and say t1/2 is equal to t? Absolutely. Yeah, you can either manipulate the equation or manipulate the numbers. Either one's fine. But what you're saying is right. You're functionally just switching these, and that's fine. Okay. So guys, you good on the math there? Okay, one last thing to talk about, and then we're done. Guys, bringing this whole idea of half-life sort of around full circle. You may remember when we originally started mucking around with this uranium, we asked the question, guys, where is that chunk of uranium headed? And what was the answer? Do you remember? Doesn't depend. Where's it all headed? The answer was this. Remember? The answer was stability. And stability is lead. But guys, the thing that we didn't talk about is this, and let me refamiliarize you. What is that? Alpha decay, mass goes down by 4, atomic number goes down by 2. What's that, dude? Beta decay, atomic number goes up by 1, mass doesn't change. Beta decay, alpha, alpha. Because the thing we didn't talk about is this. How long does it take? And guys, the answers are actually right here. I just hid them from you. So let's pull off the veil. Guys, this is how long this takes. Each one of these decay processes has a half-life. And guys, the first one, this one, is 4.5 billion years. Now, what does that mean? Well, that means that if this chunk of uranium started as uranium-240, after 4.5 billion years, half of it will then become this dude, which I believe is thorium. And guys, Ethan brought this up earlier. Let's make sure we're clear on this. It's not like 4.5 billion years from now, half of this will turn into this, and then they start going to beta decay. Guys, once turns into this, some of this immediately starts going to decay and going through the cycle. So guys, that chunk of uranium, we have elements that are everywhere along this path. The half-life simply tells us how long it takes half of them to do it. But guys, that's interesting is the range of numbers. 4.5 billion years for the first alpha. The first beta decay, the half-life is 24 days. The next beta decay, the half-life is 1.2 minutes. Then, guys, these beta or these alpha decays, which take us through number 8, go 250,000 years, 80,000 years, 1,600 years, 3.8 days, and then 3.1 minutes. Then we're down here, then the beta is about 20 minutes, and then it moves on from there. But again, guys, these half-lives don't tell us how long it takes the atoms to do this. It tells us how long it takes half of them to do it. So it's all about averages. Yeah, are you just stretching? So guys, this is how we're going to wrap up the day. Questions here? You guys okay? Okay.
How would you find the time it takes to get from uranium all the way down to?
How do they find these out? So guys, the question on the table is, Emily, is how do they know? And the answer is this. We can actually take a sample of this, and we can take and we can count how many alpha particles come out of it. That tells us. Oh, what were you asking?
How long does it take to get from the first point all the way?
Okay, you ready? Watch really close. Done.
But, yeah, that's why I was
One of them just went through the whole process and it's done. Some of them are stalled out there. Some of them are stalled out there. Some of them are stalled out there. Some of them are stalled out all the way through the process. But some lucky dudes go through all of these instantaneously and they're already there.
Just by chance.
Just that's the whole idea behind spontaneously. Yeah. Yeah, isn't that crazy?
There's also by chance that it has an
And it's a large chance based upon the half-life. Exactly. Yep. You guys good? All right. So guys, this then is your homework. We have, oh, that's nice. We have like 15 minutes to work on this. Put your hand those down. I like your hair. Josh, can I hand these to you? Yep. So guys, allow me to lend some guidance. So what you're going to find here is that through number 5, these could probably be treated conceptually. Even the ones that appear mathematical, you could probably solve them conceptually. 6, 7, and 8, those are mathematical. And guys, I'll just tell you right now, if you can't solve these, you're not ready for the test. Then guys, 9 and 10, this switches back to conceptual. Now with that said, I know that some of you, even right now, will grab your phones and pull up the answers, and that's great. But I need to tell you that Miss Call and I totally reworked this assignment yesterday, 2 days ago after school, and I have not yet created the key. So if you pull up the key right now, some of the answers are there, but they're out of order, and some of the answers just aren't there at all. So guys, give me until the end of the day. I commit to having the key done before I go home today, but if you access the answers now, they're not going to be complete. So guys, we will grade this next time. Again, we still have 16 minutes to work on these. We will grade these next time. Test is next time. Guys, also please remember, the test is the cutoff for any late homework for this unit. Please be careful. That's all I need to say. So guys, you've got to obviously do these on another sheet of paper. You ain't got space. I will print the answers and put them on the wall with the understanding that they're not complete.